So we're going to get started with a brief program today. My name's John Shepard. I'm Vice President of Sales at Julia Computing. I want to introduce sort of the brief agenda. So Viral and Stefan, co-founders of the company, CEO and CTO respectively, are going to kind of give you the Julia story. Why do we exist, and what are we doing today, and what are we looking to do in the future? I'm going to talk briefly about what our current corporate offering is. What does Julia sell? And we have two customers who've graciously agreed to give short discussion about what they do. Elton Pereira from State Street Bank and David Weiss from Conning. And those will be just short, I think, case studies of how people are actually putting Julia into production. Feel free to eat and drink if you have to eat what we bought and drink what we bought from Google. And I want to thank all the Googlers who are here because this is a great location, cool event space. They really don't have public space, but we've been partnering with Google and doing some really interesting things with some of our joint customers, and shortly we'll be on the Google Marketplace. We're going through the last steps of that iteration. So we really look forward to furthering our relationship with the Google team. So with that, I'd like to turn it over to Viral and Stefan.
Okay. Thanks, John. All right. Hi, so I'm Stefan. This is Viral. Hello. I once accidentally at a meetup introduced myself as the CEO and him as the CTO, which got gasps, and then I was like, it's actually more arbitrary than you would think. Although he's much better at the CEO stuff than I am. So I'm gonna start out with some. I thought it might be interesting to people to see some of the like ancient history of Julia and like why we started here and what was motivating me back in the day. So we went to grad school together at UC Santa Barbara, and we played ultimate frisbee for a pretty long time before we discovered that we had mutual interest in numerical computing. And then Viral taught me MATLAB, and I loved parts of it and I hated parts of it. And this was my data science stack back in 2009. So this is like 10 years ago, which is kind of mind blowing. I was using MATLAB for linear algebra, R for stats and visualization stuff, C for the fast stuff because you can't get performance out of those two languages, and then Ruby to tie it all together just because I don't know, I'd been doing some Ruby programming and it seemed better to try to send files around a cluster with Ruby than to do it with any of these other languages. And this worked. It was painful. And I felt like I had created one of these Rube Goldberg contraptions. I don't know if people are familiar with Rube Goldberg, but he draws these pictures of these inventions that do, crazy things, and somehow it all ties together. And in the end, a handkerchief waves and this guy's soup gets cooled. And you're like, oh, okay, well that worked. But so I was actually complaining to Viral while we were tossing a disk around, and he said, there's this other guy, Jeff Bezanson and Alan Edelman, and we've been talking about the same thing in a different context, but they really want to solve this problem too. And so we kind of retroactively came to recognize that the problem that we were really kicking at was what we now call the two-language problem. Also known as Oosterhout's dichotomy. John Oosterhout was the creator of Tickle, which some of you may have heard of or even used. And he thought this was a good thing. So we kind of have the perspective that it's a bad thing, but he thought this was like the way systems should be. That there was, by nature, two different classes of programming languages out there, the systems languages and the scripting languages. And they have these different, paired properties and never the twain shall meet. I think the key ones here really are that the systems languages are fast and compiled and static and hard to use. And the scripting languages are, all of the opposite things of that. They're dynamic, they're interpreted, they're slow, and they're easy to use. And he thought you should just marry the two and have a pair of them. But, we're greedy, we want, better things. So there's reasons. It's not just because we're greedy. There's actually this is a really, really good compromise, actually. I've written a lot of systems that worked with this two language arrangement, and it's
I think
pretty.
everyone here has probably done that, right?
Yeah.
It's not surprising.
It's hard to avoid it, honestly. But there's some reasons why it's not ideal. So, for convenience, you're using the scripting language. For the hard stuff, you're doing C, C++, Fortran. But the hard parts are where you would really not like a better language. So that's kind of not great. That's a bit of a bummer. And then you have to do vectorization because you have, the slow language is slow. So what you want to do is kind of do a lot of dispatch and then get out of the slow language and then do as much work as possible in the fast language and kind of stay there for a long time. And vectorization is the natural approach to doing that. And for some things it's great, right? Like writing A plus B to add to matrices is really nice. But there's other places where it's really awkward and kind of wasteful. I remember doing sparse linear algebra stuff, and you're taking your sparse matrix and pulling out index vectors and then doing some weird trick and then reconstructing a new sparse. It's a nightmare. But
I went back and looked at all the vectorized sparse matrix codes from my thesis a few months ago, and I could not make sense of what I did.
Yeah, you have no idea.
But it's sold as a good thing.
Right, but it's sold as like a moral imperative, right? Life is too short to write for loops, but sometimes a for loop was the fastest way to get it done. So, who's laughing now? It also, this is a subtle point, and this took us a while to see. It creates a social barrier. So, in a system like SciPy, there's the people who are users, and then there's the people who are developers, and they do not program in the same programming language. The people who implement the thing write C code, and the people who use the thing write Python code. And while writing Python code for 10 years will not make you a better C programmer, particularly. And I know that if I'm in one of these systems, I hit that barrier, and even though I'm a fine C programmer, as soon as I'm like, oh no, forget it, I'm not. I'd have to set up the compilation, but no, I'm not touching this. Like that's sort of where the trail stops. And so we found that by breaking down that barrier, we have suckered a lot of people who, started out as Julia users into becoming, better and better Julia developers. Some of them even making contributions. I think we're up to like 800 people who have contributed to the language. Some of it's just drive-by. Some of it is, people who are professors in something like magnetic resonance imaging, but now have, made huge compiler, changes to the language, which is amazing. There's another thing that's kind of becoming even more of a problem, which is what I probably need a better name for this, but the sandwich problem is what I've been calling it. It's just like layering lots and lots of layers of system and user code. And we're seeing this in AI frameworks a lot, right? Whereas there's like a little bit of user code that needs to be sort of layered in with all of this, all of this TensorFlow stuff. And then somehow they're calling back and forth between Python and C++, calls Python, calls C++, calls Python, and you're like, okay. If it was all in one language and one compiler could look at it, it could figure out that actually all you're doing is adding two integers, right? So we would like to solve that problem as well. So this is how Julia unifies these. I'm very proud of that animation.
Let's see it again.
Yeah, let's see it. There you go. It's the fanciest slide I've ever made. These benchmarks are actually really old now. I need to update them, but they haven't fundamentally changed. The y-axis is logarithmic, so it's how much slower you are than C. And these are just some micro benchmarks that we made up just because actually, honestly, it was because we wanted to know how badly we were doing initially. And we kept working on these until we got really good at them. And so the general takeaway is that Julia is like roughly in the ballpark of C. We're pretty happy if we're between 1 and 2, and unhappy if we're a little slower than that. At these days, it's close to 1.
It's closer to 1.
Yeah.
It's definitely closer to 1.
Yeah.
And not just on CPUs, but on GPUs and all kinds of exotic hardware.
Right. Yeah, you can. Julia is one of the few languages you can actually just directly program GPUs in. So it's pretty much Julia or CUDA type extensions to C.
Yeah.
I think this is actually the more important slide. It's the productivity. It's sort of the productivity versus speed slide. So it's lines of code on the bottom and then time It's the same y-axis as the previous slide, but you want to be in that sweet spot in the corner, like minimal lines of code, maximal performance. And I think people have done a version of this graph on the programming language benchmark shootout games thing, and it's roughly the same. It's kind of like we're in this nice sweet spot. It's not quite as extreme as this version of it, but it's where I expected us to be. So this is my data science stack today. Not that I actually do any data science. Now I just build tools, but it's Julia all the way down. So I think in taking a step back and thinking about what the ROI proposition is, if you're thinking about using Julia for business, you want to know, okay, well, what's in it for me? Am I going to make more money? Am I going to save money? And the answer is that you save money on both development and deployment. So you save money on both ends because the proposition is that you get speed and productivity and a single code to production. So this we didn't really talk about, but a lot of times what ends up happening in a 2-language system is that you write stuff in the high-level language, and then when you got to get to production, it's like, well, now it's too slow, so I got to take all of this MATLAB code or Python code and rewrite it in C++ or in Java. And then that's even worse. That's compounded if there's a loop, if there's a cycle, right? So if you had to rewrite it in C++, but now you also have to modify it and get the same people who worked on the original prototype version, they need to understand, so it can really slow down how long it takes things to get into production and then how quickly you can iterate on them. So a single language really makes a huge impact on both of those things. This is sort of new and improved in 1.3, which is in the 3rd release candidate, so pretty much out the door now. Julia has a new composable multi-threading system. And so this makes it the first high-level dynamic language that you can do this in. So you can do multi-threading in Python, but it's only one CPU because of the GIL. So we don't have a GIL. We solved this problem. It's a very, if people are familiar with Go, it's essentially the same programming model for multi-threading as Go uses. And it's been successful so far. The reports that we get are usually, holy crap, this just works, which is exactly the report you want from that.
I think in similar systems, people haven't been able to, you usually have a multi-threading either in your user code or in a package, but never sort of across the entire package stack, right? And it's just sort of not been composable before, especially in like Python or R or even, in C++, unless you use TBB or something, which I don't think anyone does. But with Julia, it's like all the package authors are now going about adding multi-threading to their packages, and now the users are also adding it to their own codes as 1.3 starts rolling out. So it's really just
nothing blows up. That's the miracle. Yeah, I mean you can use stuff like OpenMP, but then the user pretty much has to do the threading at the top, and then the libraries don't get to do the threading. And often you want libraries to be where the threading is at, because that's the code that someone has like carefully tuned and made it work extremely well on many cores. So yeah, reduced cost on both ends. That's the value proposition. So I'm going to hand it over to Viral. I have some other slides that he may or may not use as backups, but here you go.
Yeah, thanks.
I'll just stand here and like hang out as well.
So I just wanted to say a few things about Julia computing, about where we are. The biggest thing that actually some of you already have been here to this Julia Day, this version of Julia Day that happened a couple of years ago, and it's we wish we had done a few more of these, but we expect to be here more often now. Julia computing's come a long way in these last 2 years. The company's existed for about 4 years now. Until about last year when we shipped Julia 1.0, and we not Julia computing, but the larger Julia community, the focus was literally just get 1.0 out. And so even at Julia computing, our focus was to work with the community and get 1.0 out. Once 1.0 came out, we just saw this huge inflection point in terms of the user base. In fact, I was just looking through our stats yesterday, and we see almost 8,500 downloads of Julia on a regular basis. And we're now up to a total of 10 million Julia downloads so far. which is, I think, phenomenal. Like none of us expected it when we were tossing around that frisbee.
Definitely not.
And as 1.0 came around, we started seeing a lot more use of Julia in the enterprise. We have some of our customers here who are going to talk about it. I also wanted to give a shout out to Miles Lubin, who's the author of one of the first most popular Julia packages, Jump. Miles, if you want to raise your hand. Miles is now at Google and continues to push Julia in all sorts of new applications here. So as Julia 1.0 came around, we started thinking about, what's our enterprise strategy and how do we, build a successful, sustainable open source business model. And that's sort of the journey that we've embarked upon over the last year or so. Now, in the meanwhile, what has happened is that the company has grown. Since many of you would have last seen us, we are now at about 35 full-time people. We actually have well-formed, departments. We have sales, we have marketing, we have sales engineering, we have product engineering, and then, of course, the part that all of you are familiar with, which is the open source contributors part of the company as well. And it's been just amazing to go through this journey to put out 1.0 and to actually evolve the company to this stage in a sustainable way. While we've been doing this, we've also been, while we're building the business, figuring out our product strategy, figuring out the product market fit, and I'm not going to sort of say a lot about it myself because John is just going to tell you guys a lot about it and our customers are going to speak about it. What I wanted to say a little bit was that while we are figuring out our enterprise story and while customers are beginning to use Julia in production in a big way, we are also pushing the envelope on all the interesting things that our community wants us to see. So whether it is in machine learning, running Julia on TPUs, we already spoke about GPUs, whether it's in differentiable programming, making sure that every Julia library and package and user code can be automatically differentiated and put into a machine learning loop or optimized, or whether it is, whether it's things like multi-threading or distributed computing. It's, we're pushing together on all these fronts. And just seeing amazing progress. And as a company, we continue to invest in these new technologies and we make it easy to bring all of these advances to all of our customers going forward.
It's a little less sexy, but one of the things that we've been pushing really hard is package management and reproducibility. So Julia's package manager was very much inspired by things like virtual env and Nix, and sort of the basic idea is that instead of having to the entire system have to agree on these are the packages that are installed and that we're using, and then if you install and upgrade things over here, you break things over here. Each project has its own environment, and you can just have a manifest file that records all the versions of everything, and then that's good forever. And that's been very successful. We're pushing it further. We've taken care of snapshotting and keeping track of the Python or not the Python, the Julia source code level.
We should be able to start keeping track of Python.
Well,
as well,
I mean,
actually.
that's actually has been talked about because Python is not helpful in this situation. But the thing we're working on next is getting it to be data artifacts and then binary artifacts for libraries. And I think once we get to that point, which we're very close to now, you can just snapshot this is what we were using and it's perfectly reproducible, which is kind of the holy grail. But we also support that in our products, so that's one of the that's the key thing for your private code.